So the first step always we want to put down what is given to us that may not appear in our free body diagram. In this case, that angle of 20 will appear. The weight of 200 will appear. So really, given here, I would just write the diagram. There's really no extra information that we are given that won't appear in the free body diagram step. Right, so that's easy enough. We're going to take that picture and turn it into a diagram in the third step. Before we get there, what are we asked to find? Here, it's pretty explicit what we need. We need the tension or the force generally in AB. And what we name it here is important because we want to be consistent throughout the entire problem. We want the tension in AB, the tension in BC. And now we need to write our free body diagram. So we need to first choose what's the object we're going to isolate, what's the piece we're going to treat as a particle, and isolate it from everything it's connected to. So let's start there. What is the object of interest for this problem? Right, if we look at that ring at B, we have rope AB attached to it, BC, we have BD, which is going to be holding that weight. So point B is going to be our object of interest here, and we're going to be representing all of the forces that are going to be acting on this point. So this is my point B. I want to establish a coordinate system here. I get to choose it, so I'm going to choose that x is positive right and y is positive up. Now I have to represent all of the forces that act on point B. So what are applying forces to B? We are drawing what happens to B. We're not drawing what B does to other things. So what is acting on B that we need to represent in our free body diagram? Right, so we can start with the weight of the motor. We know that we're always making the assumption, unless it otherwise is stated, that gravity is going to act in the vertical direction. So the weight of the motor is pulling down on B. So what does the motor do to B? It's going to apply a force that pulls B down. It's trying to force B down, so in the negative y direction. And we know with what force it's trying to pull it down. In this case, it's the weight of the motor, 200 pounds. So the motor tries to force B down, or tries to accelerate B down. Right, what other forces are going to act on the ring at B? All right, the tension, so which one first? Right, so there's a rope connected to B that goes to A, and a rope at B that's connected to C. Ropes can only hold tension. You can't push a rope. You can only pull on the rope. So we know that the rope is going to be pulling along the direction of the rope. So instead of drawing the rope, we're going to represent the force in the rope that's pulling on point B. So from A to B, or from B to A specifically, there's going to be a force, the tension in rope AB, that pulls on this ring. We know for a rope or for a cable that the force has to act along its direction. So because the rope is at a 40-degree angle, TAB is also at a 40-degree angle. Likewise, the rope from B to C can only pull on our object. I'm going to name it TBC, and that's acting 20 degrees from the horizontal. All right, so our free body diagram, we have our point of interest, we have our coordinate system, we have labeled forces, and we have dimensions, these angles here. So this would be our complete free body diagram we need to solve this problem. Also looking at, we have TAB in the picture, TBC in the picture. They also appear in the find, although that's not necessarily always the case. We might be looking for things that are not forces, so they would not appear in a picture. So here, I recommend going with that scalar approach. We know that when we look at our diagram, if we sum all the x components of forces together, it has to be equal to 0 because our object has no acceleration in the x direction. So we know it's equal to 0, and now we write all of the forces, or all of the x components of forces that we have. So looking at our free body diagram, how can I start writing my right-hand side here? Well, let's start there. Hold on. All right, so TBC cosine 20. Again, like we were doing before when adding vectors, TBC is going to have a horizontal component and a vertical component. The horizontal component is what's going to appear in this equation. So the horizontal component of TBC is going to be its magnitude times the cosine of 20. So TBC cosine 20, that's just the amount of TBC acting only in the x direction. All right, so that's the only part of TBC that acts there. What else is acting in the x direction? Right. So TAB will have a component in the x direction. In this case, it's the cosine of 40 is the horizontal component, and it's negative, as we saw before, because it points in the negative x direction. I said x was positive right, it points to the left, so that's why it's going to be negative here. And then does anything else act in the x direction? Right, we have this other force, but it's only along the y direction. So this is my complete first equation. I have two unknowns, I have one equation so far, so it's not yet solvable. So I'm going to just put it aside for now and come back to it in my solve step. And the writing of equations and the solve step, you can kind of go back and forth among them. I usually try to solve as soon as possible, but here I'm just going to put it aside for the moment. I can write a second equation because the same thing is true in the y direction. So what are the forces that act in the y direction? Again, referring back to my free body diagram.
Positive TBC sine 20.
Right, so the vertical component of TBC is acting in the positive y direction. You wanted to add a force.
The tension of BC, plus tension of AB.
Yeah, so AB also, so we look here, it had a negative x component. However, AB has a positive y component. So in this equation, we will be adding TAB sine 40. Right, so these are both positive because both of the tensions, according to our coordinate system, have positive y components. Yeah. We are worrying about the weight of the engine, so this we do have to compensate for. When I say we ignore the mass of the object, when I say we ignore mass, we don't care about the weight of the ring itself, because it's going to be very, very small compared to the tensions and this engine. So this weight we do want to include. Yeah.
So you just take that weight times the gravity?
Well, this is in pounds. Pounds is already a force, so it's just going to be 200 pounds. And it's pointing in the negative y direction, so it's a negative 200. One thing, I didn't get to it in the notes, but pounds is a force, newtons are a force, kilograms are a mass. Nowhere in these equations is mass mentioned. These are only forces. So if something is given to you in kilograms, you do have to convert it to its weight, which will be measured in newtons. All right, so equation 2 is complete. We have those same two unknowns we had before, and this is a constant term, so we're okay. So if we look at our equations, we have two equations, two unique equations, and two unknowns. So we know it is going to be a solvable system here. So in the solve step, we solve these two equations for these two unknowns. All right, so usually when I'm presenting on the board, I'm not going to go through the actual solve steps, but here I will just to demonstrate how we would do this. We can take equation 1 and use substitution here and say that TBC cosine 20 is equal to TAB cosine 40. Okay, just putting this on the left-hand side. Since I'm going to want to use substitution here, I can divide through by cosine 20. Cosine 40 is just a number. Cosine 20 is just a number. So I can say that TBC is 0.815 to 3 digits TAB. With this substitution, I can now go to equation number 2, and everywhere I see TBC, I can replace it with 0.815 TAB. So going up to 2, I would put 0.815 TAB times sine of 20 plus TAB sine 40 minus 200 is equal to 0. And what I've done is now equation 2 has only one unknown in it, TAB. So that new equation 2 will only have one thing to solve for, and I can solve that. So if I solve that for TAB, I get the TAB is 217 pounds. Again, what did I do? I plugged this in for here and then solved this for TAB. Yeah. Correct. So we'll address that in a second here. So the tension in the rope, 217 pounds in AB. I now know this as a number. I can put it back down here, and I can find BC. BC is going to be 0.815 times 217. So BC, I get 177 pounds.